All right, hello everyone. I know that people are still coming in, that's okay. We'll just let them trickle in. I'm sure they're coming in from some very interesting talks. So meantime, I'll get started. The program continues today. I know it's been a long day, but the best is yet to come. Now we have our interdisciplinary dialogue. This is something that has made PASC very unique and special. In this case, we have Bridging Quantum and Classical Computing, Insights into the Next Era of Interdisciplinary Science. In this dialogue, we'll explore the fascinating world of quantum computing and its potential to enhance classical high-performance computing, as well as to help with quantum problems. We will discuss quantum information, algorithms, parallelism, simulators, showcasing how quantum computing can address interdisciplinary scientific challenges. So with that, we're going to have an interviewer and an interviewee. First of all, our interviewer, Florina Ciorba, is an associate professor of high-performance computing at the University of Basel. She was a senior scientist at TU Dresden and a postdoc at Mississippi State University. She earned her PhD in computer engineering from NTUA in Greece in 2008. She and her co-authors have won Best Paper awards at a whole host of places. I won't list them all. And we also have our interviewee. Somewhere here we have her. Sorry, Nana Liu. I found you. An associate professor and PI of the Quantum Information and Technologies Group at the Institute of Natural Sciences at Shanghai Jiaotong University and the University of Michigan, Shanghai Jiaotong University Joint Institute. She received her PhD from the University of Oxford as a Clarendon Scholar in 2016. She is also the 2019 recipient of the MIT Technology Review's 10 Innovators Under 35 in the Asia-Pacific region. Her research focuses on employing quantum resources for quantum computation with a current focus on quantum algorithms for ordinary and partial differential equations. With that, come up and let's start the program. Thank you.
So, we will start with a talk from Nana to set the stage about quantum computing and quantum information. And then I look forward to continuing our discussion here. You may.
Okay, thank you so much, Florina. Well, firstly, thank you so much for having me. I'm really excited and honored to be here. This is one of the few non-quantum conferences I've been to. And the other thing is, also very thankful to be welcomed by the larger computing community. Because, for quantum computing, it's still very much on the peripheries of computing, but now, really trying to develop new algorithms and hopefully maybe help some of you guys in some aspects with some of your problems. So the aim of today is, I understand many of you coming from all different kinds of backgrounds, so just giving a lightning intro into what is quantum computing, like we don't know what it is, and then just a few words about what I've been doing recently on developing algorithms with applications to partial differential equations. And throughout the talks, a lot of the talks today, and I guess in the program, many of you guys are interested in this. Okay, so I just say a word about the background. So I also work on quantum algorithms for AI, which I won't talk about today, but feel free to come ask me about it later. So I used ChatGPT to actually come up with this background. Like there. So I just put in the title, and this is the background, so you can interpret that how you will. Right, so the reason you guys, are welcoming other types of infrastructures because, we have certain classical bottlenecks, right? So things, like size of chips, because, when you go smaller, you can't avoid quantum mechanics, right? So we're reaching these type of limits. Communication, right? When we think about internet and energy costs, memory, and time. And for different kinds of algorithms, for quantum algorithms, there could be some advantages in some of these aspects. But the key message that I would like to deliver today, if you haven't heard about quantum computing before, is that when the physical infrastructure, when that completely changes, and the law of physics governing that computing that changes, then the very language that we use even when we talk about algorithms, that has to change. Not to mention how we design algorithms like themselves, okay? Which is, it's a very, very different way of thinking about things. So why do we have to go through all this trouble, right, to think about these new things? It should offer us some benefit. So the poster child for the quantum computing algorithm, which some of you may have heard of, is called Shor's algorithm. So these are quantum algorithms for factoring numbers into its prime factors. And if you're able to do that, you can break RSA encryption. So RSA encryption has a security known as computational security, meaning that it's possible to break, but only if you have a large enough computer and a long enough time. And it turns out, with current, classical algorithms for factoring, then you actually require longer than the lifetime of the universe. So it's not informationally theoretically secure, but basically, right? So because you can't do it. But whereas if you use a quantum algorithm, like in theory, if you have perfect, 4,000 perfect, something called quantum bits, and I'll describe what these are later, if they work perfectly exactly how you want to work, then they can be broken quite easily, okay, in 10 seconds. But quantum things are very sensitive, okay, to the environment. There's a lot of interaction between quantum systems and the environment, and then in which case they will lose their quantum properties. And in that case, you would need error correction codes, just as you do classically, but the quantumly, it works in a more complicated way, and you need more physical quantum bits to compensate, okay? So there's redundancy. And in this case, you probably need something on the order of 20 million, okay, quantum bits, which, we're nowhere near at the moment, so RSA is still secure. And these Shor's algorithm is based on these subroutines called quantum phase estimation, and most quantum algorithms that claim up to exponential speedups, they're actually built on these kind of subroutines. So you can go on this website and have a look at other examples for your own interest. Now this is the normal story, okay? We just need to make more and more qubits, okay? But actually this is not the only way to think about computing. So this is a work I did a couple of years back about factoring and how that's achievable without so many qubits, but a single mode. Okay, so unfortunately in Switzerland we're not allowed kind of real lasers. Okay, but here, like if you have a single laser, that's an example of a single quantum mode. So this is instead of quantum bits. Okay, you can have an infinite degree of freedom, but this can still be captured by physically, right, by a physical light mode. Okay, or some other mode. But of course, you can't get something for nothing. You can't just replace 20 million with a single mode. You have to pay in terms of resources. And the payment is that you're exchanging the number of qubits for the energy, okay, of the mode as a resource. But at least this is an illustrative example to say, actually, the resources required for an algorithm really depends on how you do it, okay, and what type of physical degrees of freedom that you use. So instead of using a quantum bit, you use a quantum mode, okay, so called a Q mode. And this is like an analog way of doing computing, which is much more familiar to maybe your forebears, okay, before digital computing became powerful. But we're really at the stage at the beginning of quantum computing. So I argue we still need to think about analog systems in those cases as well. Okay. All right. So, but before I go on, okay, into examples, you might say, I don't even know what quantum computing is. Like, what makes it quantum? Right. So before that, let's step back a little bit and just ask more fundamentally, what is computation to begin with? And just very, very broadly, you can think about, it as, made up of 3 parts. Okay, so you have your input, you ask that question, and you have your algorithm, which is really a process, right? And then you end up with an output. But how do you give your input, right? Well, you give it in terms of information, but the information that you give, either, whether or not it's digital, okay, in terms of strings of zeros and ones, or analog, okay, which are these infinite dimensional, okay, systems, nevertheless, they must be embedded in physical matter. Okay, I mean, of course, there are many possible physical substrates, but you cannot avoid them, being embedded in physical matter. So information in that sense is physical. And then the question is, now when you get to your output, which is also in terms of information, then an algorithm or the process is really a transformation of information that obeys physical dynamical laws. And now the question is, what happens when that physical law that changes? Okay, so it doesn't obey Newtonian mechanics or, it's quantum mechanics. So what happens then? So let's have a look at the blue and orange and how that changes for quantum computing. And of course, the basic idea, to open up our minds and think about computation is that computation is a physical process, okay, that obeys physical laws. So then you can, enlarge, the conception of what computation means. Okay, so in terms of input, like information, what is quantum information? Okay, so if we go to quantum computing, our input also has to be quantum. Okay, so what is quantum information? Well, it comes in 2 flavors, digital, analog. I'll first speak about digital. So digital bits, everyone's very familiar with, okay, so zeros and ones. So these are distinguishable states, okay, so like black and white, on and off in a transistor, or, your, hole punched or not hole punched, tape, in a Turing model. But what about a quantum bit? Now, typically, I guess in the media, places like that, they say, a quantum bit is somehow a mixture between zeros and ones. I like to, dispel that myth. So I think it's a very bad description to say it's a mixture of zeros and ones, because it's not a case like my dress is not a mixture of green and purple. Okay, that's not what a quantum bit is. It's much better to think about it as a vector, right, that is spanned by the states 0 and 1. So you can think about an XY plane, okay, and then you have a point in this two-dimensional space. And then what's special about the XY plane in this case is that they correspond to physically distinguishable states. So they could correspond to the ground state or the first excited state of an atom, for example. Now, what is different about quantum systems that not just a real vector, right, but the coefficients, they can be complex. And this is really important because we actually, this complexity is then involved when, we exploit interference patterns to actually make our computation faster. Okay. So now if we have n of these qubits, or quantum bits, then they live in true to the power of n dimensional complex Hilbert space. So now you say, okay, this is actually really, really large space. So maybe we can take advantage of that to resolve cursor dimensionality problems. So Fraser mentioned cursor dimensionality problems this morning, okay? So these are the problems that we'll be interested in. But there's another version of information which is not talked about in computation today because digital computing, has dominated for so long. But there's also analog quantum information. Okay, so this is when instead of thinking about your space being finite dimensional, okay, either strings of zeros and ones, but infinite dimensional. And this is actually the most natural for physicists. So I'm a physicist by background, where the coefficients, like in front of your states, actually correspond to not just real numbers, but the basis, right, is infinite dimensional. So now they live in infinite dimensional Hilbert space. And you're like, well, is that really realistically possible? Well, yes, because one example of that is a laser beam. So a single laser beam is called a coherent state and lives in this infinite dimensional space. So these x's you see up there, so instead of zeros and ones, they take real values. And you think actually in real life, if you think about position and momentum, right, I mean, these are, realistic, infinite dimensional basis. Okay. And again, you can have, n of these quantum modes, and, you can design algorithms either, okay, for these analog systems, like, this, powered by one mode of light for factoring, okay, I told you before, or the qubit system, or some hybrid, or both. Okay, so we have more possibilities with that. And you can operate on it with infinite dimensional operators. So instead of the matrix language we had before, now this is, the operator language. So again, you have to use different mathematics to think about these things. Okay, so the quadrant operators, so they correspond to position and momentum, okay, operators. Okay, so now you sort of have an idea of what quantum information is. They come in these two flavors, okay, quantum bits and quantum modes. But the algorithm, the physical process, the physical law is quantum mechanics. And because we're dealing with low energy kind of systems, then it's not, quantum field theory, okay, it's quantum mechanics. And they're based on something called Schrödinger's equation. Okay, so, and the key object, okay, in Schrödinger's equation is something we call a Hamiltonian. So it's an operator that describes, the energy, okay, of the system. So long as you can embed your problem with a corresponding Hamiltonian, then you can put this naturally into a quantum device. So now comes the question, what is now the most natural problem, right, for this quantum system? They obey Schrödinger's equation and, it has quantum information as the input. Well, it's for simulating Schrödinger's equation. Okay, so this is, the most natural problem, and this was historically the first, or the reason why people were proposing quantum computers or simulators in the first place, which is that if you have a quantum system, right, what happens after, a long period of time? Okay, so if you want to do this classically, and you wanted to model what happens to n two-level systems, like an atom at two different levels, then even to embed that information to a classical vector, that's 2 to the power of n vectors. Okay, and this is not even mentioning like how to describe the dynamics. But if you want to describe that on a quantum device, you just need n, okay, quantum bits. So already you can see, this helps with cursor dimensionality for Schrödinger's equations. But Schrödinger's equation is just one particular partial differential equation. Okay, so now the question is, what about other partial differential equations? Okay, so because if you can map other partial differential equations into a type of Schrödinger's equation and not increase the dimensionality by too much, then you can efficiently simulate this on a quantum device, just as we did with Schrödinger's equation. And this is precisely like what we've done, okay? So we have a new formulation called Schrödingerization, okay? So turning non-Schrödinger into Schrödinger by adding just one dimension, okay? So this works like so far for linear, okay, partial differential equations. So if you have a linear PDE, like in blue on the left, then on the right, you see we have a corresponding Hamiltonian, okay? And then it's, and then you see a tensor product there, And what that means is that you have the original size of the system, but by increasing one dimension, physically what you're doing is you're adding one mode, okay, which is very inexpensive, right? So if you just add, one mode, and that is enough, okay? So you don't need to, there's no curse of dimensionality, okay, here. So then our philosophy, so I know, I've been to quite a few talks before and also here, and this morning we also heard, things like dimensional reduction, because there is a curse of dimensionality problem with a lot of quantum algorithms, is that, you get your, high dimensional problem, but because of curse of dimensionality, right, it's too much resources, right? So we go to the low dimensional representation, but, there are a lot of problems that you need to solve if you do that. Okay, but what we see with these type of methods is that if we change our philosophy, that because quantum algorithms, are very good in high dimensions, if you're able to map your problem and lift it right to the quantum domain and not increase dimension too much, then you can actually resolve the curse of dimensionality if you perform that on a quantum device. So we can do this for linear PDs, non-autonomous PDs, and uncertain PDs. Okay, thank you. And now I'm out of time.
Thank you so much. Thank you very much for this introduction to quantum computing. I'm definitely not a quantum scientist as yourself, and we started conversing for the last couple of years. We don't know each other, so this will be a very genuine two disciplines, interdisciplinary dialogue. And it's great that we have the privilege to include also the PASC community in this discussion. So let's start with some basic questions. You've shown a few modes or a few types of quantum information. Mm-hmm. Then if you were to build computers, which would be your favorite, analog computers or digital quantum computers? Analog quantum or digital quantum?
Yes, so I think we've been discussing quite a lot. There's a difference between personal preference, right, and where I think it will be helpful kind of in the long run. Right. So I do have a slide on this, just for PDs, just for you guys to have an idea. So typically in classical HPC, you guys are working with classical digital, right? So and then for a lot of methods, there's this curse of dimensionality. But many of you are very young, so you won't remember. They're analog classical methods. But if you want to do PDs, very often you have to discretize your PDs because analog they work for ODEs. Okay, so even if it's nonlinear, it's ODEs. So you really have to, spatially discretize into a system ODEs, and you massively parallelize, okay, to resolve them. But what about quantum? So, for example, if we use analog systems, we actually see because it's infinite dimensional, just like from the mathematics, you don't actually need to discretize anything. Okay, because by exploiting entanglement, this is something I haven't really, I didn't have time to discuss. But by having, entangled states, which is something specific to quantum, you don't actually have to do this parallelization, by discretizing because it does it automatically. Okay, so and then also the quantum cost for these is linear in the dimension, and no discretization is necessary. Now you can also use the same mathematics, but discretize your infinite dimensional operators into discrete ones, so they become matrix type problems. Okay, and then they will correspond to different, classical numerical schemes. And in this case, you can show that the cost is then polynomial in dimension, not very high polynomials, maybe quadratic, but logarithmic in, the number of discretization steps. Okay, so this just to give you a bit of background as to, why I make my choice. So now you see pros and cons. But with digital devices, there's like I said before, quantum is very sensitive to noise. Okay, so with current systems, without error correction codes, because you need a lot more qubits than we have and a lot more control over these, then we're not really capable of building them, to the sizes to actually resolve these problems. However, if you actually map them onto the analog case, so here I have a slide for nearer term. Okay, so analog quantum simulation is something that is nearer term. So if you wanted to solve very high dimensional problems, then you just need that number of modes. Okay, so for example, we're doing experiments now, with 10,000 dimensional problems, and this is just 10,000 dimensional modes which people actually have in the labs. Okay, but whereas for digital is very good for far term. Okay, because everyone knows, right? If they're very good with errors. So long as you have error correction for the bits, then for the far term it's very good. So, but because I'm a physicist, I would say my personal preference hard is with the analog because I think there are a lot of deep foundational questions in there. But for real practicality, down the line, once we have error correction, fault tolerance, then I'll go for digital.
Okay. So as we see already on this slide, you have digital quantum simulation. Then what are digital quantum experiments like? So what are the pros and cons there?
So I would say, like many people say, quantum simulation. And I think we also had a session this afternoon, which I really wanted to go to, but sorry, I was just really jet lagged, so I took a nap. But actually, so quantum simulation, people actually, they could mean two different things. Okay, so when I say quantum simulation here, I mean you actually have a physical quantum device, and you're letting that simulate your system. So think about a wind tunnel, right? Like you actually have wind blowing, right? Like in the tunnel, right? To simulate, your system. But another way, which the classical community normally talks about quantum simulations, using classical computers to simulate quantum systems, which is a completely different thing. But of course now, like with the advances like in algorithms and real quantum computers, we really need both. Because if we have quantum experiments, how do we know that they're running the way that we expect? Because there are all kinds of noises which we might not be able to describe properly. In which case, we need good classical simulators to be able to simulate what we actually expect. Okay, but of course, at the end of the day, because to take advantage of quantum, we actually need a real quantum device. And then experiments. So we're doing both experiments and classical simulation sort of together.
So that's no different than the onset or the arrival of computational science, right? Quantum computing is not an exception. It still has to follow the three pillars approach, and maybe.
Oh, that's right. Yeah. So we spoke about this last night. Yeah. So we have the experiment, but once experiment has gone, is successful enough, then we can promote that to like a simulator, right? That's something that we trust like very well, and then like on top of that, we have the theory and the algorithm that we put on top of there. Yeah.
So you talk very passionately about quantum computing, quantum algorithms. What brought you to this field? What made this an interesting research field for you?
So I was telling you, it's a bit of a long-winded kind of question because, I was always, my background is physics, right? But of course, my major was in math because I wanted to do string theory. Because when you're younger, and especially at that time, there's always this belief that, because I want to do something fundamental, I want to understand, the nature of the universe and so on. But then you're kind of brainwashed a little bit, I think, where, no, really, like, that somehow the high energy that you go, that's somehow the only route, right, to understanding. And of course, following, Einstein's, pillars, of having, quantum mechanics, even though he contributed a lot, and then general relativity, and somehow quantum gravity is, the only route, because that's the only missing piece somehow in understanding the universe. So I felt I was really brainwashed, on that aspect, but always in the back of my mind, I was telling just Florina, I think this morning, or last night, that I read, George Boole's book, like Boolean algebra, and I was very inspired by that. But this is like independently of the interest in foundational physics. And I always thought that the idea of that information is physics, but also physics is somehow information, right? That there is it's about our way of describing the world. Like Bohr also said this about what physics is. It's really our own description of the world, as if we have these machine learning algorithms in our head, and it's our way of describing things. So, but of course, our way of describing things is in terms of information. So always in the back of my mind, information is somehow central, but I didn't know kind of how to investigate that more because, I thought, okay, I have to be a string theorist, right? That's the only thing, to do. So I actually started my PhD in high energy physics. And then, I was thinking about things like ADS-CFT, for those who've heard of it. Like it's, a duality between, a low dimensional model and a high dimensional model. And then the reasoning they used to say that these are the same models is to say, well, they had this information quantity called von Neumann entropy. And they said, this entropy is the same, and therefore, they're somehow equivalent. And I thought, well, this is such a basic, there are so many different other kinds of information out there. So why do you have something so complicated, and yet the bridge is so shallow somehow? So then, it was a long-winded route. And then I actually found, so when I was in Oxford at that time, there, everyone there was doing kind of the high energy physics or condensed matter. But then, like on the very other, completely different building, that there was this very smaller group doing something called quantum information, which I never heard of like before. But because I was trying to find places where I could understand this information better. Right, so then, that went on, so I'm very much interested in foundational questions. And I guess from that information aspect, you naturally get into quantum algorithms. But that was at the time when it wasn't popular, right? Because quantum computing only became sort of popular in the last maybe 5 years or so, right? So yes, and I think and the reason I describe this journey kind of in a little bit more depth is because I think it really highlights kind of the divergence of approaches to quantum algorithms. Because the people originally interested in this, and not too long ago, they were very much interested in foundational questions. So things like, whether or not quantum computing will break the Church-Turing thesis, right? So, the Turing model was really basic, or we need something, called quantum. But whereas now it's becoming popular in the wider community because there is this promise that quantum computing can somehow become a technology, right? So it's a very different way of thinking. But then, so I think it really changes algorithm development when you still have these people interested in foundational questions, and they kind of force too much computer science thinking, I think, rather than kind of algorithm and scientific computing thinking. So I'm kind of navigating that myself right now.
Wow, that was not, as you said, a straight path, but apparently it led you to where you can think about the next fundamental research questions that you would like to address. So what are those, let's say, on a horizon of 5 years? Because you said quantum computing has become very popular and hyped in the last 5 years. So who knows what will be important to work on in the next 5? Yeah. So what are your thoughts on that?
Well, so I think quantum computing is simultaneously overhyped and underhyped. Okay, we all know why it's overhyped.
That's why it's quantum, right? In both spaces.
Yeah, like newspapers, going to solve climate change and whatever. Like, I don't believe that. Like, certainly not with the algorithms we have today. Despite all these papers, I think, it's a lot of just, advertising, false advertising. But it's underhyped in the sense that I think there are a lot of foundational questions that people are kind of ignoring. And I guess partially for the reason that, some of the quantum algorithm community is still dominated by computer science way of thinking, right? So because the field is not so old, and in fact, despite everything you hear, there are not, so many people who really focus on quantum algorithms. Because of all the grants, that come in, then whatever group they're doing, they always have an out branch that says, now I'm doing quantum. I think the same thing is happening with machine learning. Everyone's doing machine learning and quantum, right? But I'm saying the core people who are really doing quantum algorithms, they're actually not so many, right? And a lot of them, maybe they're a bit older, so then maybe they focus on, so these foundational questions where you have to prove things like exponential speedups, and if you don't, it's somehow not interesting enough, okay, or quadratic. But if you speak to more the scientific computing people, so now I'm engaged more with the classical community because I want to learn how real computers, like originally they came along, right? Because people work on a quantum algorithm, they never worked on actual computers, right? So So for me in the next 5 years is really engaging more, right, with the classical community, really understand what your problems are. Because the problem with the quantum community is more like they live in their own little bubble, right? And they say, okay, well, we're going to solve this problem. Somehow we find that if it's slightly relevant to, some, real world problem, we just write a paper about it. But really, if you look into it, and I ask people in the real world who work on these problems, they're like, I'm not interested in this problem. Like, it's not really a bottleneck, really, right? So I'm interested in talking to, real people, like you guys who have real problems. And then I say, well, are we able to help you with that? And, if quantum makes sense or not, it's not, it's not a, panacea, you just use it for everything, right? Like, I think that's just the wrong approach. So to answer your question, working more, from the scientific computing aspect, so continuing with, the PDE thing. So we do linear, but I think there's a lot of non-linear problems, and it's really very, very non-trivial, to map, because remember, Schrödinger's equation is a linear equation, right? So how do you map non-linear to linear, okay? Because if you linearize, right, there are all kinds of problems that come up. Right, so we're trying to develop, algorithms where instead of doing linearization, right, we do truncations and things like that. Then you really want to find a linear representation. So you're capturing all the, non-linearity in there, but that is very difficult. But I think that's a big challenge. So we also work on, algorithms for uncertainty quantification, stochastic problems, and also we have some experiments that are coming up. So I think in the near horizon, I feel like, because I also need to increase my own knowledge of, algorithms. So, yeah.
So from the knowledge you have so far, how does one start thinking about quantum algorithms if you want to recruit, let's say, members from this community to work with you or others like you working on quantum algorithms? How can anyone wanting to work on quantum algorithms start thinking about them?
I think, on the one hand, it's simple. On the other hand, it's not. Okay, so I say the simple one, right, for encouragement. That so for example, a postdoc that I have, and I actually have 2 PhD students, and they have no quantum background whatsoever. And within the first couple of months, they were able to write their own quantum paper, right? And so that's the easy part, in the sense that really, if you don't care so much about the interpretation of quantum mechanics, so you don't try like to intuitively understand it, but the mathematics of it is basically linear algebra. Right, so if you have a good handle on that, right? So because I described, qubits being vectors in this high-dimensional space. I mean, you guys all know how to deal with those. So if you just look at it from that abstract perspective, it's possible to actually get into the field. So I don't think it has a very high entry barrier. The hard part is really to find sort of really new algorithms, because a lot of what's been happening in the past is, people just getting classical algorithms and kind of like quantizing it, which is kind of a boring thing, I think, to do. I mean, it gets the job done, like superficially somehow, but but to really think about new ones, then it's really about integrating knowledge from, the classical community. And I think there's a, greater diversity of algorithms in the classical community, certainly than in quantum. So kind of, just chatting more and then trying to find.
So then, now that we know how to start thinking about algorithms, what applications do you expect will benefit from having quantum algorithms expressed and mapped to quantum systems? What applications? In our discussions, you mentioned that it all depends on the amount of information that is being able to be captured in a quantum algorithm to solve a particular problem. So what are those kind of problems?
So answer the first question, but which is, what type of problems can be solved? Well, so in principle, right? So every single classical problem, right, can be mapped onto a quantum device, okay, and vice versa. Okay, so it's not like one problem cannot solve another. There's no halting problem kind of difference between these two like computing paradigms. It's more that what benefit do you want from it? Okay, so that's one aspect. Like the second aspect is certainly what I'm interested in is not which problems, but like which problems are most natural for quantum devices. Okay, so which is why it's maybe much more natural to start with the physics of this. Right, so this is when you think in a more analog way rather than digital. Because with digital, you're actually missing out on all the physics. They're just kind of like tiny little black boxes you put together, which gives you universal computation, but you don't know how really that comes about so much. So so on the one hand, the kind of algorithms to look at are the ones which are natural, like simulation type of algorithms. But on the other hand, there are problems which are purely classical. Right, so like certain combinatoric problems and some machine learning type of problems if you want to use for classical data. And there, in that case, this is a big caveat which I didn't have time to mention in my talk, which is there is a huge cost, right, associated with embedding the information into a quantum device and then extracting the information from that. Right, and very often this is kind of hidden in algorithms, like because they want to claim speed-ups. But this is like another kind of area, like to kind of to think about. I don't know if that answers your.
Absolutely. So because you mentioned speed-ups, and then there is cost for encoding information into a system and getting it out of the quantum system and algorithm, then what can we expect in terms of scalability of these algorithms if you have very large quantum machines to execute them? Yeah,
I mean, so far, all these foundational algorithms, they can be like all these scaling things. They can be computed just like theoretically, right? So then so for example, in our papers, we have pretty good ideas about like what those are, right? But then I think that there's going to be a time, okay, where the real kind of quantum computers, like the physical ones, are going to be so powerful. Right, hopefully, where it's really just about experimenting with them, right? Because I guess the same thing happened with the real computers before. The famous saying, we're only going to need 5 computers in the world, right? But then we found all these other uses for them. I think the same thing's going to happen with quantum. Once we do have these, so then I can't answer kind of that, right? But at the moment, right, we can still compute. Yeah.
So. In an analogical sense, not analog sense, we know that classical high-performance computers, supercomputers, exhibit more and more levels of parallelism, right? So in a hierarchical fashion and in an increasing fashion at the different hierarchy levels. So can we think about quantum problems and quantum systems in the same sense? What is parallelism in the quantum computing world?
So I'd like to dispel another myth, which is, so there's this idea that, somehow because quantum, states are mixtures, right, between bits, which you now know it's not, then somehow it's, just the power of it just comes from parallelism, that you're actually performing all these computations at the same time, okay? In which case, then, a parallel classical computers can just do better, right? So, and this is a myth, because actually this is not where the full power, of quantum computing actually comes in, where, how you get these exponential speedups, for example. So it's really, so if you remember that I had these alphas and betas, right? So if you're describing a quantum state, then these alpha and betas, that can be complex valued, okay? And the significance of that is now what happens when you change the basis, right? So instead of zeros and ones, like x and y's, you rotate, okay, the x and y, axis. And then you're going to get, differences, right, between alpha and beta, okay? But then the probability, okay, of you, being in these states, they're actually the absolute value squared, right? Which means that if there's a phase difference, right, between alpha and beta, like that actually comes in the final probability. So all that means is that because of interference effects, you can kind of think about, you might have heard quantum things, they're both like particles and waves, okay? So if quantum things are like waves, right, then waves interfere, like they constructively interfere and they also destructively interfere. So when they destructively interfere, somehow the wrong answers get cancelled out, which is very different from what happens in classical parallel computing. Mm-hmm. So that is a myth I wanted to dispel. So that's one aspect in which quantum is not, right, just the same as classical parallelism. But then there's another parallelism, is that, once you have quantum computers, maybe you want many of those, right, that are together in something like a quantum internet. So this is something I also worked on. And in that case, then there are different classes of these networks, right, of, parallelism, because, what kind of communication do you allow, between your quantum systems, right? Do you allow only classical communication channels, or do you also allow quantum communication channels, right? And then these would give rise to, different, models of, this distributed computing or parallel computing.
Okay.
And this is not, very well investigated.
Okay, so you're inviting the audience to start thinking about it, so that's a great thing. So when we start building exactly those large distributed quantum computers, for the classical large distributed supercomputers, so we have a ranking list, right? So it is in our nature to put peoples in bins, and quantum computers on a ranking scale, supercomputers on a ranking scale. So what would such a list, given that there are many companies producing quantum computers with different modalities, right? What would a list like that contain, or how would we rank them?
Well, I guess if you think about the list as a quantum superposition, then everyone can be happy. Like no one is, first or second. I think it's very hard to say, because classically, you have a very good idea, right, of what you want already, right? But quantum has so many problems, like in terms of the physical machines. Mm-hmm. So, and of course, people always show off to say, oh, now we have, X or Y number of bits, qubits and so on. But that's not a good indicator, or, whether or not they're going to actually solve your algorithms, because they can be extremely noisy. Actually, most of them are, especially the higher the number, you have to be very suspicious, right? But not just, the noisy of, them in themselves, because that's just a memory. You have to perform operations onto these, right? So once you perform operations, again, the gates that you perform, they can be, extremely noisy, because it's not just about having, very high dimensional systems, but it's really about, how long you can perform the computations, right? So that's called the depth, okay, of the quantum circuit, right? And if you want to perform meaningful algorithm, it needs to, be depth. But then, quantum systems, there's decoherence, meaning they become more and more classical, like very quickly over time, right? So then you have to do things a lot faster. So there are a lot of parameters that are involved that are kind of hidden, in these, top lists. I'm sure it classically happens as well. But again, we have to keep in mind that a lot of what happens, like you see in the media with all these lists, it's not like purely scientific, right? A lot of it is really, there are, political, kind of, things happening, to give certain impressions, right? So that's something important to keep in mind, I think. Yeah.
Thank you very much. I think that's a very nice food for thought for the community. And I would like to ask the community, the audience, if they have any questions for Nana. We have 5 more minutes. Yes, please. You have a microphone next to you if you want to use it, or just...
Okay, I hope it works. Yeah, I was wondering, you were saying that the RSA example, that if you have 40 perfect qubits, it would break in 10 seconds. How do you come to...
4,000.
Oh, 4,000, yeah. But how do you come to the number 10 seconds? So
Oh, yeah.
I have a hard time of understanding what's happening there. Is that
So
one operation per
it's
second?
myself,
Or?
by the way. Like, so that's a caveat right there. Yeah, so there are quite a few assumptions that go in, right? But what you can do is that you can calculate the number of gates that are required, and then you have an estimate for how long it takes for you to do each gate, right? So that's the short answer. But I didn't actually come up with those numbers, so I got them off somebody else. Yeah. So, but actually, some people might argue we can do better than this. But this is just to give like a basic idea.
Mm-hmm. Yes, please. There's one question in the back first. Yes.
Okay, thank you very much for this insightful presentation. You mentioned this qubit and all this information. One thing that I didn't pick up, apologies if you mentioned this, is how do you come about at actually constructing these machines, and what are kind of the resource limitations that we're currently facing today from constructing more of these quantum computers, and what are the things that you think at the margin, or let's say being eased, so that the newer computers can be constructed now with more capabilities? And okay, thanks.
Sorry, I think I missed the first word.
Just how do you build these quantum computers? What are the limitations, the resource limitations?
Oh, like to build distributed quantum computers, or
to construct the computers, the quantum computers.
Oh, like the individual ones, not the distributed system.
Yeah, well, whatever the parallel to high-performance computing clusters would be.
That really depends on the physical system that you use, right? So right now, classically, you guys decided on silicon, right? I mean, of course, now you're going beyond that, but quantum is at the very beginning, right? So you might have heard of, the most popular one right now is superconducting systems, but there are also photonic systems, and then there are, ion trap systems, neutral atoms. So each of these have their own constraints. So it's very hard to kind of answer like in general. It's quite individual. So all of these, they have their pros and cons. So there are some systems where interconnectivity is much simpler, like then the qubits can actually talk to each other more easily, right? But then you might not have, be able to have very many, right, compared to others. So then it depends on what kind of algorithms you want to perform on these and so on. So yeah, so it's very complicated.
There was one question there, and then we move to you. Yes.
Thanks for the nice talk. The term analog computing is nice to hear again. I mean, 1970s was a high time of analog and analog digital hybrid computing. And I was just thinking, there is such a huge amount of nearly forgotten literature, how to interface digital and analog devices. Do you think it might be helpful to, dig it up?
Well, I have been doing exactly that. I'm very passionate about analog because for a physicist, right, because I had to learn about qubits, right, because I came from, string theory. So, when you first learn about quantum, you hear about wave functions, right? This is the first thing you hear. But, what is this guy, right? So if you go back to this U of x, that's a wave function, actually. But somehow if you go to the quantum information community, they're like, oh, what on earth is a quantum mode? And I'm like, that's a wave function. Right. So, so for me, because we're at the very beginning, we're at the very motherboard kind of level, right, of computing, then you're really dealing with the physics of these systems. So you really have to think about, what is the physics of what's happening? And, the wave function is just, very, very natural, because now if you go into the digital picture, you're losing the physics. Right? I mean, even classically, you actually don't know what you're mapping. So with all these numerical schemes, if you're looking at a circuit, you have no idea if you're solving Fokker-Planck, right, or a heat equation, right? But whereas for the analog, so the beauty of, I think the formalism that, we're doing here is that if you express it in an analog way, right, if you look at this Hamiltonian, right, A of 2 and A of 1, right, they're the Hermitian and anti-Hermitian components of this A of t that's in your original linear differential equation. So just by looking, right, at the physics of what's happening, right, that you want to simulate, so we can do Fokker-Planck, we can do Black-Scholes, we can do all these linear PDEs, or the linear forms of these PDEs, then you automatically get like this form, like on the right, right? So analog, like for me, it's not just about like near-term feasibility, right? I mean, this is how I, sell it, right? Because of people who are interested in technology. But at heart, I'm more of a, foundational person. I'm really interested in, what it means to compute, right? And what it means to simulate. Because here you're, transforming one physics problem into another. And I think that that's really deep. So I think, the depth of analog computing, it goes beyond, right? Just the technological kind of benefits of that. So I've been digging up a lot. If you know more analog literature, I'd love to discuss this. And I know Peter is also very interested in analog. So I hope if there are more people here, by the way, who actually do classical analog or interested in that, please come and I really love to chat about that because there's just not enough people to talk to about this. So, as you can see, I'm very desperate. Yeah.
So we have time for one last question, please. Do you have a microphone? Yeah.
Hi, yeah. So my question is about, I think we're going to be able to use noisy quantum bits for something useful at some point, given the amount of investment and money that is poured into the noisy quantum bit systems. But do you think it's feasible to have the perfect qubit? Is there something realistic is going to happen at some point?
Well, so what I mean by perfect qubit, is I just did it in a short way, you have to really think about the information. You just want your information to be perfect, right? So this is why people are designing something called quantum error correction codes rather than classical error correction. So the simplest error correction classically is just like redundancy. You just have a lot of them, right? And then you just apply a majority vote kind of thing. So I mean, it's a bit more complicated in quantum. Right, so when I say perfect, what I mean is you have many physical qubits that represent the same information as one quantum bit, and it's perfect in the sense that if there are errors, you're able to correct for them. But there's also something on top of that called fault tolerance, which means that the protocol you apply to correct for these errors, they're going to get more errors, right? So you don't want those errors to be greater than whatever you put in. So once that threshold has been passed, the errors you incur in correcting for it is not as big as what you have originally, then that's when you get fault tolerance. Yeah. So, but that requires a lot more effort. So people, I mean, in my opinion, despite what you guys have seen in the news, I don't believe it. So what they have right now is error corrected quantum memory, right? But if you want actual, you need to perform gates, right? And I don't think that has been shown convincingly, right? That you can do those in a fault tolerant way. But I feel like, once that kind of threshold has been passed, and that is a very, very difficult threshold, so we don't really know exactly how many years, maybe a couple of years, maybe 10 years, I have no idea. But once that once that threshold has been passed, then, the advance can be exponential. It's gonna, So it's gonna change overnight, basically. Yeah. I think. I don't know.
So this is the time where I would like to thank Nana very much for her talk, for the discussion, the audience for the questions, and you again for the answers. And let's congratulate Nana.